Well, hello there. I've got a question for you. How do we know that water is H2O? You've probably been wondering the same thing ever since you started chemistry, ever since you first learned the formula for water. How do we know that in each molecule of water there are 2 hydrogens and 1 oxygen? How did we count those things? Well, the way that we do that is by splitting apart the substance and weighing the parts. Here I've got some water in a beaker, and there's a battery attached to some wires, and I'm using electricity to split the water molecules into their 2 elements. If you look really closely, you can see some little tiny bubbles there on each of those wires. Let's see if you can see those. I'll get a little bit closer there. Let's see if you can see the bubbles. There's some bubbles right there on the other side too. Those bubbles are hydrogen and oxygen gas. Now, if we could collect those 2 gases, we could weigh them. And if we can weigh something in chemistry, we can count it by using the mole unit. That's what we're going to be looking at in our next experiment. How do we find the chemical formulas for substances, and how do we compute their chemical formulas from splitting the parts and weighing them? Okay, please make sure that you have a copy of the assignment, Empirical Formulas, a calculator, something to write with, and also a periodic table. What we'll do is we'll begin by looking at the examples that are on the front. How do we know that water is H2O? And then on the inside, I'll do a demonstration and show you how to do the lab procedures that you'll follow when you come and work on the lab in class. So, looking at the example problems. First example we'll look at is, how do we know that water is H2O? Suppose we had 2 grams of water, and we divided it using that technique I showed you with electricity into the 2 parts, hydrogen and oxygen. And we weighed how much hydrogen and how much oxygen there was. What we'll do is we'll take each of those 2 elements, how many grams there were, and we'll convert that into moles to count how many atoms there are. We set it up so that units cancel, that the grams that were given cancel out with the atomic mass, the formula mass, the molar mass, the mass of 1 mole of oxygen, or the mass of 1 mole of hydrogen. And when we do the math, we multiply across the top, 0.22, and then we multiply times 1, and then divide by the bottom, 1.0080. And when I do the math, since I have 2 significant figures divided by 5 significant figures, I'll only keep 2 significant figures in my answer, which will be 0.22, so 0.22, and the unit will be moles of hydrogen, because grams cancels out grams. And then I'll do the same thing for oxygen, 1.78 times 1 divided by 15.999, and the calculator will give me a lot more digits than I can keep. Since I have 3 significant figures divided by 5, I'll keep only 3 significant figures, 0.111, so 0.111 moles of oxygen. Now what I've done is I've counted how many atoms of hydrogen and how many atoms of oxygen were in the 2 grams of water that I split apart. But what I really want to do is compare them in whole number ratios. So to do that, I'm going to pick which one of these 2 is the smaller one. And that's this one, 0.111. I'm going to divide both of them by the smaller one. And the reason I'm doing that is because then this turns into a 1. Something divided by itself equals 1. And then this one divided by this one, 0.22 divided by 0.111. Let me do that again. 0.22 divided by 0.111. And I'm going to round to the nearest whole number. 1.98, the nearest whole number is 2. H2O1. That's where we get H2O from. H2O1. For every 2 moles of hydrogen, there's 1 mole of oxygen in the 2 grams of water that I divided. This works for any amount of a substance. So for example, if I had more water, let's say it was 50 grams of water, and this time I divided into this much hydrogen and this much oxygen, again the same way using electricity, I'll take the grams of each of those elements and I'll turn it into moles. I'm doing that by using the molar mass of the substance, which I found looking at the periodic table. I'll multiply across the top 5.50 times 1, and then divide it by 1.0080. And the calculator is going to give me a lot more digits than I can keep. I can keep 3 significant figures, so 5.46 moles of hydrogen. And then for the oxygen, I'll take 44.5 times 1 divided by 15.999. And the calculator gives me again more digits than I can keep. I can keep 3 significant figures, not the 5. And I'll write down 2.78 moles of oxygen. So in the 50 grams of water, there are this many hydrogen atoms and this many oxygen atoms when counted in moles. But I want to express it in a whole number ratio, so I'm going to divide both of them by whichever one is smaller and round to the nearest whole number. Anything divided by itself, of course, is 1. And if I divide 5.46 by 2.78 and round to the nearest whole number, 1.96 would round to 2. So again, it's 2. H2O. No matter how much water you have, it's always the same ratio of moles. To find out the formula for any substance, all you have to do is break it down into its parts and weigh them, and then convert those parts into moles using the molar mass for that part, and then express it as a whole number ratio by dividing through all the parts by whichever one is the smallest, so that its whole number is 1, and then the other ones are all multiples of that. What we're going to do is an experiment where we try to find out the formula of a compound that contains water. It's called a hydrated compound. Let me show you how that one works. Okay, please look with me on the back of the first page. At the top it says demonstration, and I'm going to demonstrate the procedures for finding the formula for a compound called nickel sulfate, NiSO4. This is the compound, nickel sulfate. It's a greenish looking substance. It consists of crystals of nickel sulfate, and attached to the crystals are a specific number of water molecules. This substance is made by doing the chemistry in a solution of water, and then the water is evaporated, leaving the crystals behind. But some of the water stays stuck to the crystals in a specific ratio, and that ratio becomes part of the formula for the compound. We're not going to break down this compound all the way to its elements. That's extremely difficult to do. Instead, we're going to count how many parts there are for each one nickel sulfate crystal, or part of the substance, how many parts are water. And we'll try to find out what the question mark is, what the coefficient is for that formula. So the steps are, first, to take a clean, empty crucible and to weigh it on a balance. And when I weighed this crucible, it was 25.64 grams. And then pouring the substance in, you need about a good scoop or so. This weighs 35.64 grams. And so I purposely use this amount, because then when I calculate the mass of what I just put in there by subtracting, it's exactly 10.00 grams. When you do the lab, it probably won't be an exact number like that, but I chose that number for a reason. Then what we're going to do is we're going to take the substance and we're going to heat it over a flame, and that will make the water evaporate. Just like boiling water out of a pot, you can heat the water out of the compound. And then we can weigh it again to find out how much water was lost, and we can separate the compound that way. Okay, so I'm going to put this substance in the crucible over the fire, and as this heats up, the water molecules will be driven out of the compound. And this one, since it starts with a color and it loses the water, it's going to change color very gradually. It'll start turning a lighter color, a yellowish, whitish color, and that will tell us that all of the water is gone. Depending on which substance you use in the experiment, you may or may not see a color change. If you use the white compound, magnesium sulfate, you won't see any color change because it's already white. But if you use the copper sulfate compound, which is a blue material, you'll see a change in color. It should turn a light blue, almost white. So we'll let this one heat for a while until it completely loses all of its water, and then we'll weigh it again. Okay, you can see that the color has pretty much completely changed because the water in this substance has all evaporated, leaving behind the dehydrated compound nickel sulfate. The next thing I'll do is I'll reweigh this, and then we'll do some calculations. Okay, now that the water has been heated out of the compound, we can reweigh this to find out how much of the dehydrated substance is left and how much water was removed. When I reweighed this, it was 29.74 grams. And so subtracting shows that the amount of the dehydrated compound that's in there now, the yellow stuff that's left behind, was 5.90 grams. And subtracting to find out how much water was removed is 4.10 grams. So these add back up to the 10 grams that I started with. 5.90 of those grams were the dehydrated stuff, the yellow part that you see left behind, and this many grams, 4.10, that's how much water was removed. So if this is the mass of each of the parts of the compound, what we want to do next is turn that into moles so that we can count how many parts of the compound were in the formula. So the next step, we'll convert the grams of water into moles of water. We had 4.10 grams of water, and to turn that into moles, we'll use the molar mass. That 1 mole of water is 18.015 grams of water. I set it up this way so that units would cancel. Anything in the top and bottom of a fraction reduces to 1 and cancels out. And so now when I do the math, if I multiply 4.10 times 1 divided by 18.015, when the calculator gives me the answer, I'll only keep 3 significant figures because that was the fewest significant figures in my measured quantities, 0.228 moles. So 0.228 moles of water. That's how many water molecules I removed from the compound. I also need to know how many pieces of the nickel sulfate were in there. So the next step is to do that. However, I need to know what is the molar mass of the nickel sulfate. I need to know 1 mole of nickel sulfate equals how many grams of nickel sulfate. So I list the elements, nickel, sulfur, and oxygen, and count their atoms in the formula. There's 1, 1, and 4. And then I'll use my periodic table to find the masses of each of those elements. So here's nickel and sulfur and oxygen. Nickel is 58.71 atomic mass units, and sulfur is 32.064 atomic mass units, and oxygen 15.999. When I multiply, I'll keep as many significant figures as there were in the measured quantities, because counted numbers don't have significant figures that I need to worry about. Multiplying by 1 is easy. Multiplying 4 times 15.999, 4 times 15.999, and I'll keep 5 significant figures, 63.996, 63.996. Last step, add them all together. So 63.996 plus 32.064 plus 58.71 equals, and the calculator gives me this answer. The answer on the calculator has 2 after the decimal point. Let's see how many can I keep. I can only keep 2 after the decimal point, since this was my weak link in the calculation. When you add or subtract, you keep the fewest places after the decimal point. So this is convenient. I can write 154.77. That's the molar mass, or the mass of 1 mole of nickel sulfate formula units. Now, let's see, how much did I actually have? I had 5.90 grams. So given 5.90 grams of nickel sulfate, I'll multiply by 1 mole of nickel sulfate on the top, because I'm trying to find moles, and the grams will go on the bottom. 154.77 grams of nickel sulfate. I set it up this way because then units cancel. Anything in the top and bottom of a fraction reduces to 1 and factors out. And then I can do the math. 5.90 times 1 divided by 154.77 equals, and I've got 3 significant figures that I can keep, so 0.0381 is how many I can keep. 0.0381. So 0.0381 moles of nickel sulfate. That's how many pieces of nickel sulfate were in the compound, and compared to how many waters there were in the compound, now I can find out what is the chemical formula of the substance. So let's put it all together. We're going to find the nearest whole number ratio of the dehydrated compound, the yellow part, the nickel sulfate part, compared to the water part. So there were 0.0381 moles of nickel sulfate, and there were 0.228 moles of water. And I'm looking at those to see which one is lower. This one is lower, so I'm going to divide both of them by the smaller one, 0.0381, 0.0381. And when I do that on this side, since it's divided by itself, it will equal 1. And over on this side, 0.228 divided by 0.0381. And I'll round to the nearest whole number. If it says 5.984, the nearest whole number there would be 6. So this equals 6. It's a 1 to 6 ratio of parts. Nickel sulfate and 6 hydrate, 6 waters. Let's check the answer and see how close I came to what it says in the real chemical formula. This is where I got the nickel sulfate from. It says right there, nickel sulfate, 6 hydrate. So that's the chemical formula. That's how we find the chemical formulas for substances. We take them and we break them down into their parts, and we weigh the parts separately, and then we turn that into moles to count them, and then express it in a whole number ratio. So just to review what I did, I took 10 grams of substance, divided up into the crystal part and the water part, and then I turned those into moles. First I counted how many waters there were by turning it into moles, and then I counted how many nickel sulfates there were by turning it into moles, and then I compared those moles and turned it into whole numbers by dividing both of them by whichever one was smallest. The smaller one turns to 1, and the other one turns to another whole number, and those are the parts of the chemical formula in the end. What you'll do in the experiment is to do the same process with different compounds, and those compounds will either be magnesium sulfate or copper sulfate, and you'll try to find out how many water molecules there are in its formula using the exact same procedures. So use this as your guide. And then when you're done, there are problems on the very last page of the assignment that you can work out using the same steps as I showed you on the beginning demonstration for water.